If you are somewhat like me, there probably was a point where you wanted to add rigid bodies to a cool project you had been working on. Naturally, you go on YouTube and seek for a video that explains 3D rigid bodies. Of course, you don't want to use a library because that's really unsatisfying. But you find nothing. It's either not about rigid bodies, only 2D, not detailed enough, too basic, a Blender tutorial, or even too theoretical. So next you go to Google because even though you hate reading, maybe there was some good article about it. After pushing aside some Blender, Unity and 2D rigid body tutorials, at some point you finally find the holy grail. The notes of the physically based modeling SIGGRAPH course by Andrew Witkin and David Baraf. But what is this? You decide to give up. What I've just told you was actually me a few years ago, even though I might have already given up after finding no YouTube videos. But now, having attended lectures about the stuff, I felt confident enough to try it again. This time, I didn't give up. And if you allow me to get a bit technical today, I am extremely excited to welcome you to my 5th devlog episode. So far, I only worked with point masses, a mass concentrated in a single zero-dimensional point. While it might sound pretty uninteresting, when using multiple of these and connecting them, you can actually create pretty cool effects. However, enforcing all of these connection constraints is pretty expensive and doesn't necessarily lead to the complete rigidity like I need for the wheel rim. This is why I wanted to use a different simulation model, the rigid body. Instead of a single point in space like for the point mass, a rigid body is an entire region, omega, of the 3D space. Every point in omega is part of the rigid body, which is an infinite number of points. What makes the body rigid is that for any two of these points, their distance is always the same, regardless of the body's state. It can be moved or rotated, and the distance remains the same. Technically, this two-point distance definition also allows an exact reflection of the model, but since this is not very realistic, it is explicitly excluded here. To get a bit more comfortable with this continuous rigid body concept, let's look at how its mass can be computed. One of my professors often joked around by saying something like, mathematics is just a race with an infinite number of elements. And I think this analogy applies here too. If our rigid body was made of discrete chunks that each had a volume Vi and a density ρi, you might already be able to see how its total mass can be computed. Density is just mass per volume. So to get the mass of a discrete chunk, its density is multiplied with its volume. The total mass of the rigid body M is then just the sum of all of the discrete chunk masses. To arrive at our actual continuous rigid body definition, we make these discrete chunks smaller and smaller, and eventually, with the power of math, we define an infinite number of them, each shrunken down to a different point x. Because of this definition, each point x still has an infinitesimal volume dv and a density ρ of x associated with it, just like the discrete chunks. To compute the total mass, the sum is converted to an integral over the domain omega of the rigid body, since dv approaches 0 in the limit case. Ρ of x is now a function of space and has a value for each point of the rigid body. Integrating it over omega means integrating it over the volume of the rigid body, resulting in the total mass. Later, we need to cover a few more of such volume integrals, but with this correspondence between the continuous and the discretized version of the problem, I think it's much easier to understand. Though you might be wondering how to even perform this integration if x is our variable, but supposedly we are integrating v, which is nowhere else to be seen. This is because the notation here is a bit of a simplification. Actually, we are integrating over the 3 dimensions of omega, and the differential dv is just dx, dy, dz. If our vector bold x is now defined to be xyz, the integration makes a lot more sense. First, ρ is integrated in the x dimension, then in the y dimension, and lastly in the z dimension, though the exact order doesn't matter here. The simplest example would be to integrate this for a centered, axis-aligned cuboid with constant density and side lengths a, b, and c in the x, y, and z directions respectively. The domain omega of this cuboid is just a negative halved side length to the positive halved side length for each dimension. And since the density is constant here, it can be factored out. Solving the integral by first integrating x, then integrating y, and lastly integrating z, the volume of the cuboid a times b times c is obtained. To no surprise, the mass of the cuboid is its constant density times its total volume. So now that we have a better understanding of what a rigid body actually is, let's look at how to describe its motion in 3D space. We know from physics that there are a few quantities that are always conserved. For example, we know that the boost, well, I actually meant the conservation of the linear and angular momentum, which are relevant here. What this means is that for any rigid body floating around in space and not interacting with anything whatsoever, its linear momentum and its angular momentum are conserved exactly. Their values do not change. Let's start with the linear momentum. From high school or probably even middle school physics, we know that the linear momentum p of a point mass is defined like this. It is equal to the mass and the velocity multiplied. Describing p in a very unphysical way, I think of it like the amount of movement power the point mass has. On impact, small values of p don't have much of an effect. However, large values of p cause lots of destruction. Additionally, the velocity is a vector, so p is a vector too. For a closed system of multiple point masses, their total linear momentum is just the sum of the individual linear momenta. So for each point mass I, its mass mi and its velocity vi are multiplied and then summed with the other ones. The rigid body is similar, but it has an infinite number of points. So like before, instead of a sum, we use an integral over the domain omega. You can think of this to be the mass and this to be the velocity of the point. Again, you can see the correspondence between the finite sum and the integral. Let's see if we can simplify this expression and gain some more insight into rigid bodies. The velocity is just the derivative of x with respect to the time t. For the next step, it's easier to not use dot notation. Two things are of importance here. First, the derivative is a linear operator, so it can be distributed over sums, or in this case, the reverse. However, for this to be applicable in our case, the derivative would have to be taken for the whole expression and not just x. Luckily, this doesn't matter because the density and mass of the object are independent of time, so their time derivatives are zero and not relevant. The derivative can be applied to the whole expression and thus be factored out. Next, the expression is multiplied by 1, the total mass of the object m divided by itself. This is done so that the mass in the denominator can be distributed to the integral terms. It might not look like all of these seemingly random conversions helped, but let's think about what this integral represents here. Conceptually, for each point mass x of the object, we multiply it with its mass divided by the total mass, and everything is summed up. So each point is weighed by the percentage of its mass in relation to the total mass. The resulting expression is the center of mass x cm of the object, cm for center of mass. As we'll see, the center of mass is a very important property of a rigid body and later in code just denoted by a variable x. As a last step, the dot notation can be reintroduced. Now, you might ask yourself, why is this of any use? We did all of these conversions just to arrive at the linear momentum equation similar to that of a point mass. But that's actually the exciting thing about all of this. There are two key takeaways. First, even though a rigid body is way more complex than a point mass, its linear motion can still be described just by the velocity of its center of mass. So although the motion of the rigid body might look like this, to describe the linear part of it, the position of the center of mass and its corresponding velocity is all we need. The second important thing this equation implies is that an unconstrained or force-free rigid body always rotates around its center of mass, because a general rotation around some other point would make the center of mass move in a nonlinear fashion, which would require an acceleration that can't be present in an unconstrained rigid body. Before diving into the angular motion of the rigid body, let's already look at how this can be implemented. I defined a struct rigid body that currently only stores the world position of its center of mass x, the corresponding velocity v, and the mesh it consists of. To avoid letting things get too complicated too quickly, we'll use an axis-aligned cuboid with side lengths a, b, and c as the mesh that is centered in its local coordinate space and has a constant density of 1. Before we can do anything, we need to know where to draw the mesh. We have the position of the center of mass given as x, but where is that position inside of the mesh? To compute its center of mass, we can use this formula we just saw. Though we just want to compute this once at startup, so no time dependence needed here. Because the density is a constant 1 and the mass of our cuboid is constant 2, they can be factored out. As an exercise, you can expand the integral and solve it like in the beginning of the video, but I will now spoil you that the result is 0, meaning the geometric origin of the model aligns with its center of mass. This means we can just draw the cuboid mesh at the position x that is stored. Having the center of mass align with the geometric origin of the mesh is quite a desirable property, since it simplifies a lot of things like drawing and specifying rotations. So later, when dealing with more complex meshes, we want this to be the case, or at least pretend it to be. Now let's say we have some starting position x of 0 of our cuboid and a velocity v of t and want to simulate its linear motion. In code, the setup could look something like this. We define a rigid body cuboid and give it some starting values for its center of mass and its velocity. This kind of problem we are trying to solve is known in mathematics as an initial value problem. We have the initial value x of 0 and want to compute the following x at every possible time capital T using the derivative of x. Intuitively, you might already know the exact code that is needed to solve this problem. Just add delta time times the velocity to the position. But where does this code come from? Well, the time derivative of the position is the velocity. If we integrate both sides from 0 to the specific point in time capital T that we want to know the position of, and then solve the integral on the x dot side, you can see that the position appears. But to compute it, we need to integrate our velocity from 0 to t as well. While this is very easy to do in this specific code example with a constant velocity, it is a problem in the most general case where the derivative depends on the variable that we are trying to compute. You'll see an example of this later when we talk about the angular motion. For now, just imagine that the integral can't be computed analytically. So instead of computing the exact position at the time t in a single step using analytic integration, we perform a step-by-step numerical integration. We start with the current position x of 0 and velocity v of 0. Then we pick a small step size delta t and just assume that the velocity doesn't change that much over the course of this step. This way, we approximate the exact value of the small part of the whole integral by a simple box. The next position x of delta t is then just the previous position x of 0 plus the approximation. Exactly like in the code. The approximated constant velocity is multiplied with step size delta time, and because this approximates the positional delta of the step, it is added to the position. The resulting position is the starting position of the next step. So then we pick the velocity at delta t and assume it to be constant again. The position is again updated with the area of the box and the procedure continues until we stop at some time t. At the end, we have an approximation of the integral value here. Each of the intermediate step results can be displayed, or if the step size is too small, only a few of them could be displayed. As you can see, the code that adds delta time times the velocity to the position just approximates a small part of the integral value. In this case, it's the simplest numerical integration method there is, the first order explicit Euler integration. Higher order explicit Euler integration schemes improve the accuracy of the result by choosing a better approximation of the function than just a box. However, for the sake of completeness, regardless of how high the order is, explicit Euler schemes tend to have stability problems that make the simulation explode. This is why there are other methods, such as the implicit Euler scheme, for example, which can be proven to be unconditionally stable. It works by using the velocity of the next step for the current step. But as you can see, this is way more difficult if the velocity depends on the exact value that we are trying to compute in this case. Also, while the explicit Euler method tends to increase the system's energy, the implicit method tends to lose the system's energy. So they each have their up and down sides. But for now, let's stick to the first order explicit Euler scheme and figure out how to implement it. First of all, for readability, I broke up this code here and put it into two separate functions. One for setup and one for simulating. Then, my simplified game loop is as follows. There is a struct context where all of the game's state is stored, like our rigid body cuboid or delta time, which stores how long one frame, or specifically one game loop iteration took. When the game starts, I do a bunch of setup, including the creation of one context instance named context. The relevant part here is just the setup of the cuboid. While the game is running, I gather inputs, render the next frame to the display, and compute the time that all of this took and store it in delta time. A good place to perform the simulation in is here. The latest user input has just been processed, and after computing the next simulation state, it can directly be visualized. So we can just perform our integration using delta time, right? Well, this works, but there are two problems. First, to make debugging easier, it would be nice to have a deterministic simulation that doesn't depend on some random delta time variable. Second, if delta time becomes very large, for example because the rendering took very long, then the simulation takes a huge step instead of many small ones, which is very bad for the approximation and can potentially blow everything up. So instead of using this delta time, I used a step size h that is constant. To keep the simulation time and the game time synchronized, I defined this additional time accu variable inside the context struct. It accumulates the time which the simulation is running behind the game time by adding the past game time before simulating. Then the simulation can be stepped as long as it is running behind by more than one or exactly one step size. Great, now our cuboid can move through the scene at a constant velocity. However, while this is correct, it isn't really any more interesting than the simulation of a point mass, since as we've proven, that's essentially the same thing. Move the center of mass like a point mass and draw the rigid body at this position. The one thing that point masses don't have, contrary to rigid bodies, is an orientation. So let's get to the interesting part and talk about rotations. We want to find a way to describe the angular equivalences of the linear position and velocity, which are the orientation and the angular velocity. You might already know ways to describe the orientation of an object. There are quite a few of them. For example, Euler angles, an axis and an angle, a rotation matrix, or a quaternion. It seems though that in simulations, mostly rotation matrices and quaternions are used. And for this episode, we'll stick to the rotation matrix. R essentially just describes the rigid body's local coordinate system using an x, y, and z vector. But since rigid bodies are only allowed to be moved and rotated, there are a few restrictions imposed on it. Each of the vectors must have length 1, such that no scaling happens, and they need to be perpendicular to each other, such that no shearing happens. Both of these restrictions are summarized by letting R be an orthogonal matrix. Additionally, the vectors need to be oriented in such a way that no mirroring happens, making the determinant of the matrix positive, or in this case equal to 1, because of orthogonality. All restrictions combined reduce the 9 degrees of freedom of a general 3x3 matrix to just 3, an orientation. As we have proven earlier that unconstrained rigid bodies always rotate around their center of mass, it makes the most sense to let the origin of R be the center of mass. Again, it's handy if the geometric origin of the mesh aligns with its center of mass. This way, I just needed to add an additional 3x3 rotation matrix to the rigid body struct. In the rigid body's unrotated state, the axes align with the ones of the underlying coordinate system. When the rigid body is rotated, the axes just follow this rotation. What remains now is the angular velocity, typically referred to as omega. It is just a vector that points in a direction around which the rotation is performed. For this omega, for example, the rigid body rotates like this. All points move on circular paths that are oriented perpendicular to omega. To determine the rotation direction for a given omega, you can use a right hand. Make your thumb align with the same direction as omega, and then your fingers curl in the direction of the rotation. The speed of the rotation is encoded in the length of omega, in radians per second. For example, if it is 2 pi, like here, then the object rotates with 1 revolution per second. Storing omega is as simple as for the orientation. I just added a vector omega to the rigid body struct. And now rigid body rotations can be implemented, right? The rotation matrix is initialized to the identity matrix, and omega can be any vector, like this for example. However, when trying to translate the linear integration formula to angular variables, we run into a problem. R is a rotation matrix consisting of 9 values, while omega is just a vector made up of 3 values. They cannot be added. The problem here is that unlike in the linear case, where the position is just the derivative of the velocity, the derivative of the rotation matrix is actually not omega. To discover the correct relation between the two, let's first look at how a single point r of the rigid body is rotated by the angular velocity omega. Also, let r be defined relative to the body's center of mass. The effect of omega on r looks like this. What we are seeking is the derivative or the velocity of r given r itself and omega. Since the path of r is a circle, maybe you can already guess the direction of r dot. It points from r in the direction that is tangent to the circle, meaning it must be perpendicular to r and omega. You know what that means. The cross product strikes again. R dot points in the same direction as the cross product between omega and r, because this way it is perpendicular to both of them, like required. But by how much does r dot point in this direction? Since r dot is the velocity of r, its length tells us how far r travels per second, or more precisely, the length of the arc that r travels per second. Now, the length of omega tells us that, but in terms of radians per second rather than arc length per second. So how to convert from radians to an arc length? This is where the beauty of radians comes to shine, because the arc length of some a radians is equal to a in a unit circle. For a circle with arbitrary radius, a just needs to get multiplied by the radius. Similar to how you compute the circumference of a circle by using 2 pi radians, because that's a full revolution. If we insert the length of omega in here, the result is the arc length that r travels per second, which is exactly what we needed. We're almost there. The last remaining unknown is the radius of the circle that r travels on. It is the length of the part of r that is perpendicular to omega. As you can see, this is a right triangle, where this is the angle between omega and r. This means that the radius is just the length of r multiplied with the sine of this angle. So the length of r dot becomes this. Extremely convenient, because by definition of the cross product, that is also the length of the cross product between omega and r. Putting everything together, r dot points in the direction of the cross product between omega and r, and its length is the length of the cross product between omega and r. Meaning r dot is just a cross product between omega and r. Okay, technically it could also point in the exact opposite direction, but since I told you that the rotation is defined by the right-hand rule, you can use the definition of the cross product to figure out that this is the correct order. Again, we are in a situation where you might ask yourself how this helps us in determining the correct relation between the derivative of the rotation matrix r and omega. But if you think about it, the axes x, y, and z of the rotation matrix are like the vector r, just direction vectors that are rotated by omega. So the matrix derivative is composed of the velocities of each one of these axes. And we now know how to compute these by using the cross product. Nice, there we have the relation between omega and the derivative of the rotation matrix. To make this formula a bit more compact, we can factor the cross products out using the cross product matrix, denoted by the superscript cross. Finally, r appears again. We are now ready to make the rigid body rotate. Similar to the linear case, omega cross times r is multiplied with delta time and added to the rotation. The computation of the cross product matrix can be implemented like here, for example. As you can see, the rigid body rotates around omega. Unfortunately though, we are not done yet, because this is not how the universe works. Do you remember how we derived the linear motion of the rigid body from its linear momentum in the beginning of the video? Conveniently, in the linear case, because the momentum is conserved, the velocity of the rigid body's center of mass is conserved too, if we assume the mass to be constant. However, while the angular momentum L is a conserved quantity, the angular velocity omega actually is not. One of the more popular examples of that circumstance is this screw thing here you might have seen in this video by Veritasium. Every 3 seconds it turns by 180 degrees, so omega can't be constant. Another example of this would be if you try to flip your phone like shown here. While it is certainly theoretically possible, what will most likely happen is that you won't exactly turn it around this axis, but a slightly misaligned axis. Like the screw thing, your phone will flip while spinning. So I'm sorry to tell you that, but the creators of this universe want you to endure even more math now. To make the simulation correct, let's start with the angular momentum L, because we know that that is a conserved quantity. For a single point r that is relative to some origin, its angular momentum is the cross product between r and its linear momentum p. Please note that I decided to drop the time dependence of any variable to make the following easier to read. The linear momentum is just the mass of the point mass times its velocity. For the whole rigid body, we again integrate this expression to take every point into account. Previously, we saw that the velocity of r is just the cross product between omega and r. Now, what we have here is the vector triple product, similar to the scalar triple product. The vector triple product can be rewritten to this expression. Substituting a, b, and c in our case, we get this. The dot product of r and omega is just a scalar, so this r can be moved to the other side. Next, matrix multiplications are commutative, which is why these parentheses can be moved. Since omega is independent of r, it can be factored out. However, because this is a scalar, we have to insert an identity matrix here to make it work. Finally, the relationship between the angular momentum L and omega becomes apparent. To obtain L, the left side of omega must be multiplied with the so-called inertia tensor or inertia matrix of the rigid body. While the computation of this matrix is a bit challenging, understanding what it means is comparably simple if we break its properties down step by step. The following derivations are going to get a bit rough, but if you go through it all, I promise it will make sense at the end. First of all, you might have asked yourself, if L is conserved and omega is not, could this mean that the inertia tensor changes too? And indeed, this is the case here. It will become apparent once r of t is rewritten to be just the time-independent initial r rotated by the current rotation matrix r of t. To simplify this expression, let's first remove these brackets. Next, we apply the transpose of both of these terms here to their individual components. This matrix multiplication is just the identity matrix, since the transpose of a rotation matrix is also its inverse. Similarly, we convert this identity matrix to almost the exact expression we just removed, but this time the transpose is on the right-hand side. Since the dot product here is just a scalar, it can be inserted in between the matrix multiplication. Lastly, if these two brackets here are moved, we can notice something. Both of these expressions here are encapsulated by r from the left and r transpose from the right. The matrices can be factored out. And now it looks almost like the original inertia tensor, just as r here is a bit annoying. However, actually the r doesn't have any effect. If you think about it, rotating the object doesn't change its density at any of its positions. So this notation here is a bit of a simplification, because in reality this row here is dependent on r, thus cancelling any rotation we input here. R can be removed if we instead use the initial time-independent density. What does all of this tell us? As you can see, we have two versions of our inertia tensor. The first one here is completely time-independent, since all of its variables are time-independent as well. It is the initial inertia tensor of the rigid body in its unrotated default state, like how it was exported from Blender, for example. As soon as we start to rotate the rigid body, the time-dependent inertia tensor is obtained, which is also part of the angular momentum equation. But, and this is the good part about it, as we just derived, the integral doesn't need to be re-evaluated, which would be quite expensive. Instead, we can just use this formula here to get the rigid body's global inertia tensor at any point in time. Though of course, the initial inertia tensor I0 must still be computed. For that, it might be easier to look at the actual matrix that is integrated instead of these compressed expressions here. The first one is the dot product of r with itself, resulting in the length of r squared. The second expression is known as the outer product of r with itself and results in this matrix. There isn't enough space to expand the first matrix in place, but it's just the length of r squared on every diagonal entry, and the off-diagonal entries are 0. Combining the two matrices is now straightforward. Because the second matrix is being subtracted, their diagonal entries cancel with the corresponding parts on the diagonal of the first matrix, and the off-diagonal entries just negate. This is the expanded form of the initial inertia tensor. There is unfortunately no magic trick that simplifies this expression, so each one of these 9 values that you can see must be integrated for a given rigid body. If you didn't care about any intuitions, you could stop here, compute I0 and use all of the formulas I've shown to complete the simulation. And we'll do that for our rigid cuboid in a minute. But what exactly does the inertia tensor mean now? To understand that, let's look at the global inertia tensor again instead of I0. The only difference being that R might have a different orientation. On closer observation of the matrix, we can deduce a few of its properties. First of all, the matrix is square because it has the same number of rows than it has columns, namely 3. Second, I assume you would agree that all entries of the matrix are real, so no complex numbers. Lastly, the matrix is symmetric, meaning it is equal to its transpose. All off-diagonal entries are mirrored along the diagonal. In summary, the inertia matrix is a square, real, symmetric matrix. That means it has a special eigenvalue decomposition. Here, U is like R, just another rotation matrix. You may have noticed that it looks very similar to our previous decomposition here. The only difference now is that it is an eigenvalue decomposition, so this lambda is a diagonal matrix. However, that doesn't change the fact that U and R are both still variable rotation matrices. So if we apply the knowledge of this decomposition here, in particular that I0 is an inertia matrix, then lambda must be an inertia matrix too. Just a very special one, because it is a diagonal matrix, meaning that all off-diagonal integrals are 0. Finally, we can make sense of the inertia tensor. Imagine you had 2 wheels with exactly the same mass, but one is small and the other one is large. You can turn the small wheel no problem, but the large wheel is way harder to turn, even though both have exactly the same mass. This is because the mass of the larger wheel is further distributed from its center of mass. Specifically, the difficulty to turn the wheel increases with the square of the radius of the distribution. And looking at our decomposed inertia tensor, it's the same thing, just that we have 3 values instead of 1, because for every rigid body there are 3 principal axes which are stored in this U matrix. Each one of the diagonal values here encodes the inertia value for one of these principal axes. For the x-axis, for example, only the squared length of each perpendicular yz vector is important. Conceptually, they get multiplied with their respective mass and are then summed. That's the inertia value of the principal x-axis. Looking at the object from the direction of each one of these axes, we can even make out how large each of the inertia values must be. The smallest distribution can be seen for the y-axis and the largest one for the x-axis. The z-axis is in between. The actual inertia values confirm our hypothesis. X is the largest, then z, then y. So these values tell you kind of how hard it is to turn the rigid body exactly around their corresponding principal axis. If you wanted to turn the rigid body around the principal x-axis, for example, your turning strength, so to speak, would have to be divided by the inertia value of the x-axis to get the speed of the resulting rotation. In the case of an arbitrary axis, the x, y and z components of the axis would have to be divided by the inertia values of the corresponding principal axis to get the resulting rotation axis. Now, this is where we can even get an intuition for the angular momentum vector L. Because the arbitrary axis I was talking about, you want to turn your rigid body around, actually is L. We can see this if we reorder the equation for L into an equation for omega. Just multiply both sides with the inverse of this matrix from the left. Apply the inverse by reversing the multiplication order and distributing it to each element. Lastly, the inverse of the rotation matrix is just its transpose, and the inverse of the transpose of R is just R itself. And that's the equation for omega. Ignoring the rotation matrices for a second and applying this formula to our eigenvalue decomposition, we can see what I was talking about. L is the direction you want the rigid body to turn around. But because of its mass distribution, some principal axes are harder to turn, so each component of L is divided by the corresponding inertia value to obtain the actual resulting rotation, omega. Maybe you can already see now why the inertia matrix is multiplied by rotation matrices from the left and the right. We always want to scale L along the principal axis of the rigid body. But since L is defined in global coordinates, just scaling each of its components would scale along the global coordinate axis, which is not what we want. Like I said, we want to scale L along the principal axis, which are stored in this U matrix. So first, L is rotated into the eigenvalue inertia coordinate space to obtain a local description of L. Then it can be scaled like we want to get a local description of omega. Notice how in this example, omega is most reduced in x direction, because that's the largest inertia value of the rigid body. Finally, this local omega is rotated back to global coordinates to obtain a global description of omega. Summarizing this in other words, the inertia matrix does not describe a coordinate system that transforms one coordinate space into another, like often seen in computer graphics. Rather, you can simply think of it like a correct scaling operation along the axis of some arbitrary orthogonal coordinate system. I hope that gave you a good intuition as to what the inertia tensor and the angular momentum really are. I spent quite a long time thinking about this, but in my opinion, this is a good mental image to have. At least that's what I think about. I will make use of the eigenvalue decomposition of the initial inertia matrix in the next episode. For now, it was just a concept to help us make sense of the matrix. Let's use all of the gained knowledge to make the previous code physically correct. All I needed to add for that was the correct angular velocity omega instead of the previous constant one. And now we know that omega can be computed using this relation, where the angular velocity L is conserved. Thus, it makes sense to store L for our rigid body instead of omega. And like I said, L is just the direction around which the rigid body wants to turn around, so it can be set arbitrarily. The last unknown here is the inverse initial inertia tensor I0. Since our cuboid is axis aligned, the process of computing it is not as difficult as it might look. It works just like the mass computation I showed in the beginning of the video. The density of our cuboid is constant 1, so we can drop it. Furthermore, the integral can be expanded to the 3 coordinate axes. The vector r tilde is just defined to be x, y, z, so its components can be replaced. Lastly, to actually compute this for our cuboid, we insert the bounds of its domain, which does only work so nicely because the cuboid is axis aligned. It does already look much more approachable, doesn't it? It's a good exercise, so I encourage you to do the computation by hand. I will just present you the solution. Here, V is the total volume of our cuboid. If we didn't remove ρ in the beginning, V would now be the total mass of the object. Interestingly, this matrix is diagonal, which means that the coordinate system of an axis-aligned cuboid aligns with the coordinate system of its principal axis. Translating this into code, there is no need to store the zero value of diagonal elements, so I0 can be stored as a vector. Also, only the inverse of the inertia tensor is needed, so why not directly store its inverse? For the computation of the inertia tensor, I wrote this small function here. It takes the side lengths of our cuboid A, B, and C as input, first computes its total volume, and then returns the diagonal of the inertia tensor. In setup, I called this function and inverted the result to be able to store the inverse inertia tensor of the cuboid. Lastly, the simulation code needs to be changed to use the correct omega instead of the constant one here. For the computation of omega, the rotation of the cuboid R and its inverse inertia matrix are needed. This function here just places each of the 3 values in inf I0 onto the diagonal of the otherwise 0 initialized matrix. With that and a function that transposes R, the correct omega can be computed. Finally, after all of these derivations, the cuboid was rotating correctly. To convince you and myself that my derivations are actually correct, I cloned the Bullet physics library from GitHub and compared the results of my code to the results of their code. Though in between cloning Bullet and running it, there was one issue. I had to compile and link it to my program. And if you know me, that's a big problem. The compilation of Bullet itself seemed to work, but then I tried to build and run one of Bullet's own example programs. I am telling you, I will probably never figure out how to do this correctly. After a bit of self-soothing, I found these holy files in the source directory and thus rejected the idea of using the CMake generated libraries. These files were like a lifebelt for me because they allowed me to compile Bullet by hand. And if you ignore the horrible C++ code that integrates Bullet into my program, here are the results. Both versions are overlaid. I would say that looks pretty synchronized. Up until a certain point. The Bullet simulation is the transparent overlay, so it appears a bit ghost-like. You can see that my implementation seems to run faster than the Bullet one. This is because the determinant of R is rising slowly, which violates the rigid body's property of not being scaled and means that R is actually not a rotation matrix anymore. In Bullet, the determinant always remains 1. The effect is even more dramatic if the time step is increased to say 33 milliseconds instead of 1 millisecond. You can clearly see how the increasing determinant also scales the cuboid. Until eventually the rotation matrix explodes. One quick fix here would be to re-orthogonalize R after each simulation step. In a future episode, we will see another, better approach to handle this problem using quaternions. And specifically in the next episode, we will find out how to compute the inertia matrix of any triangle mesh instead of just a cuboid. In fact, writing this from scratch is so much work that it will probably fill the whole next episode. If you want to have a small preview of what's to come, you can look at my implementation of the Jacobi eigenvalue algorithm on GitHub. But for now, that's it. I have not uploaded the code I presented today to any GitHub repository because it's part of my game, which is not open source yet. But maybe I'll create a small program for the next episode. By the way, with this video, the lines of animation code of all my episodes combined total to roughly 6,700 now. So I am almost at the number of lines of my game, which are about 7,800, including blank lines and comments for both of these numbers. Isn't that crazy? So now you know why my game progress is so slow. I spend way more time making videos about my game than I actually spend writing the game, because writing animation code is not the only thing I have to do to create these videos. Let me know what you think about my intuition of the inertia tensor. Thanks for watching.